So picture this. You are watching a screen, right? And there is this massive cylinder of metal just plummeting back toward Earth from the edge of space. The engine ignites, these huge flames billow out, and then, I mean, impossibly, this towering skyscraper just gently sets itself down on a tiny platform in the middle of the ocean.
It really looks almost fake when you see it on video.
Yeah, exactly. We have all seen the videos of these rocket landings, and honestly, it is so easy to underappreciate what is actually happening. Like, it looks like it's just falling slowly. But it is this chaotic, fiery balancing act of shifting weight, explosive power, and, millisecond timing. It is, without a doubt, one of modern engineering's greatest magic tricks.
Oh, absolutely. It's a total illusion of simplicity.
Well,
But it looks like this really gentle touchdown on the outside is actually a violently complex negotiation of physics on the inside. You are looking at thousands of variables being solved simultaneously, while the vehicle itself is, well, it's fundamentally changing its own mass as it falls.
right. So welcome to this deep dive. Our mission today is to unpack the mind-bending physics and the software that makes SpaceX's Falcon 9 rocket landings possible. And to do this, we are drawing from a highly detailed technical paper dated June 28th, 2026, titled Merlin Engine Thrust Regulation Mechanism.
Yeah, and the authors of this paper really get under the hood of the Merlin 1D engine. They move past the whole spectacle of the landing to explain the specific mechanical and computational hurdles of actually surviving that descent.
So why should you care? Because if you have ever been amazed by those landings, this deep dive is going to shortcut all the heavy math to give you the ultimate aha moments about how this actually works. We are going to see exactly how you control a continuous explosion well enough to parallel park it. So, okay, let's unpack this.
Oh, good.
Before we can even talk about the brilliant mechanical solutions, we have to establish why throttling a liquid-fueled rocket engine is such a nightmare for aerospace engineers in the first place.
Right, we have to start with the fundamental physical constraint here, which is the weight problem. A rocket's mass drops dramatically as it burns fuel. Like, when the first stage of the Falcon 9 separates from the second stage, it weighs about 22 tons.
Okay, 22 tons.
But by the time it reaches the ground for landing, it is burned through so much propellant that it only weighs about 10 tons.
Wait, so it loses more than half its mass just on the way down?
Yeah, exactly. And to manage that descent, the Merlin engine has to execute 3 very specific burns, and each one has completely different thrust requirements based on that changing weight.
Right, because 22 tons falls very differently than 10 tons.
Exactly. So the first is the boost back burn. This happens right after separation. The rocket needs to brake and literally turn itself around to head back to the landing site. At this point, it is still really heavy, so it needs 100% thrust. That is about 845 kilonewtons of force.
And just to give you a sense of scale, 845 kilonewtons is roughly 190,000 pounds of thrust. That is significantly more powerful than a single engine on a Boeing 7777. You are unleashing commercial airliner levels of power just to slam on the brakes in a vacuum.
Yeah, it's a massive amount of force. Then comes the second burn, the re-entry burn. The rocket is hitting the thicker parts of the Earth's atmosphere, and it needs to slow down so it doesn't just burn up from friction.
Right.
So for this, the engine needs to throttle down to about 50 to 60% of its maximum thrust, which is outputting roughly 420 to 500 kilonewtons.
So we're dialing it back because the rocket is getting lighter, and I guess the atmosphere itself is doing some of the braking work for us at that point.
Precisely. Which brings us to the final stage, the third burn, or the landing burn. By now, the rocket is nearly empty, sitting at that 10-ton mark. To achieve a soft touchdown, the thrust must match the rocket's remaining weight with near-perfect precision.
Okay, so how low do they have to go?
That requires the engine to throttle down to exactly 39 to 40% of its maximum thrust, which is about 330 kilonewtons.
Wow. It sounds like driving a massive 18-wheeler that suddenly sheds its trailer and turns into a lightweight passenger car while you're going down a highway, but you still have to use the truck's massive diesel engine to park it.
That is a surprisingly accurate way to picture it, actually.
Now, if you are driving a high-performance sports car and you just starve the engine of fuel at high RPMs to slow down, it stalls and sputters out.
All right.
I'm guessing a rocket engine doing that is a bit more catastrophic. Like, why is it so hard to just restrict the fuel flow?
Well, what's fascinating here is that a rocket engine is this finely tuned, incredibly fragile ecosystem of pressure. If you just reduce the flow of liquid oxygen and kerosene, you completely ruin the pressure dynamics inside the combustion chamber.
Oh, so it's not just about less fuel equaling less fire.
Right. When the pressure drops too low, you trigger what engineers call combustion instability. The fuel basically stops vaporizing into a fine mist. Instead, it pools or it burns unevenly, and the flame starts vibrating violently. And those acoustic vibrations can literally shake the engine apart in milliseconds.
Wow, okay. So you can't just trickle the fuel in. It has to be atomized and sprayed with immense force, regardless of whether you are at 100% power or 39% power.
Exactly.
And the stakes during that final landing burn are astronomically high. The paper actually notes that if the thrust misses the rocket's actual weight by more than 5%, it crashes. It either slams into the concrete or it accidentally starts flying back up into the air, runs out of fuel, and then drops.
Yeah, there's zero room for error. And beyond just the raw force, there's the delicate chemistry of the explosion itself. You have to maintain a vital mixing ratio between the liquid oxygen and the kerosene. The optimal ratio is 2.6 parts liquid oxygen to 1 part kerosene. The safe operating range is between 2.0 and 2.7.
So the actual recipe for the explosion has to stay within that incredibly narrow window while the total volume of fuel is dropping by 60%.
Exactly. If your flow rates get sloppy when you throttle down and you drift outside that ratio, you are in immediate danger. If the ratio goes too high, meaning too much oxygen, you get an oxygen-rich fire. Under high pressure, superheated oxygen acts like a cutting torch.
Oh, wow. So it just burns the engine.
Yeah, it will literally melt and burn right through the metal walls of the engine in seconds. If the ratio drops too low, it runs fuel-rich. That is safer for the metal, but it creates massive amounts of soot and instability, which drops your thrust unpredictably.
Okay, here's where it gets really interesting, because when I was reading the section on how SpaceX solved this, I couldn't believe they basically pulled a piece of Apollo-era technology out of the archives.
Oh, yeah, it's such a cool detail.
Because you can't just starve the engine without melting it or vibrating it to pieces. They couldn't use traditional rocket engine showerhead designs.
Right, so they revived the pintle injector. It was originally used on the Apollo lunar module's descent engine, the very engine that allowed Neil Armstrong and Buzz Aldrin to hover and throttle down before touching the lunar surface.
Which is wild to think about, because a traditional injector is basically a showerhead with fixed holes, right? If you turn down the pressure, the fluid just weakly dribbles out. But this pintle injector is totally different.
Completely different.
The paper describes a 3D printed central post that sticks right into the combustion chamber. The liquid oxygen shoots straight down the middle of this post axially. And then the kerosene shoots out the sides of the post radially. They collide at a 90-degree angle right at the tip.
And the genius part is the mechanical sleeve that moves up and down over that post. When the flight computer demands a reduction in thrust, they don't just reduce the fuel flow, they physically move that sleeve to shrink the size of the gaps the fuel is spraying out of.
Oh, it's exactly like putting your thumb over the end of a garden hose.
Exactly.
If you turn down the faucet at the house, the water volume drops and the stream goes limp. But if you press your thumb over the nozzle, you restrict the opening, and suddenly that tiny bit of water is spraying out at high pressure again. Right. It atomizes into a fine mist.
That is the perfect analogy. By changing the physical flow area, the pintle injector keeps the pressure drop stable. The engine targets a 20% pressure drop across the injector no matter what the thrust level is.
Okay, so the pressure is always high.
Right, because the pressure stays consistently high at the point of injection. The fuel and oxygen atomize perfectly into that highly combustible mist. It completely avoids the combustion instability we talked about, even when the engine is running way down at 39% power.
That is just brilliant hardware design. But creating a stable explosion is only half the battle. We also mentioned that running an engine like this can literally melt the combustion chamber walls. I found the thermal management section of this paper absolutely wild. Like, they are using highly flammable jet fuel to cool down an incredibly hot engine.
Yeah, it sounds like a paradox. It is a technique called regenerative cooling, and it's a phenomenal hardware hack. Before the kerosene is ever injected into the combustion chamber to be burned, it is pumped through a network of tiny pipes built directly into the walls of the combustion chamber and the nozzle.
Wow.
So as the engine burns and generates massive heat, that heat transfers into the metal walls. The cold kerosene flowing through those tiny pipes absorbs the heat, cooling the metal down to safe temperatures.
And as a thermodynamic bonus, the kerosene gets preheated before it enters the chamber, right? Which makes it vaporize and burn even more efficiently when it finally hits the pintle injector.
Exactly. It's a win-win.
But cooling the main chamber isn't even the hardest part, is it? There's a massive thermal challenge with the turbopump.
Oh, the turbopump is a nightmare to manage. It is the mechanical heart of the engine. It forces the fuel and oxygen into the chamber at insane pressures. During that first boost back burn, the turbopump is screaming at 22,000 revolutions per minute.
22,000 RPM.
Yeah, but for the landing burn, it has to aggressively shed momentum, dropping down to about 12,000 RPM.
And the turbine blades inside this pump are made of a super strong nickel alloy called Inconel 718. But even Inconel will melt if it gets too hot while it's spooling down. To power this pump, they have a smaller, separate combustion chamber called a gas generator. And the way they keep the pump from melting is completely counterintuitive.
It really is. They intentionally run this gas generator incredibly fuel-rich. We're talking a mixture ratio of just 0.355.
Wow, so way below that 2.6 optimal ratio.
Drastically below it. All that extra unburned kerosene isn't there to combust. It's there to absorb heat. By flooding the gas generator with excess fuel, they drastically lower the temperature of the exhaust gases that hit those delicate turbine blades. They happily sacrifice a little bit of fuel efficiency just to ensure the turbopump doesn't melt into slag during the landing sequence.
Okay, so we have a shape-shifting Apollo showerhead and fuel that acts like antifreeze. But having an engine that physically can adjust its pressure doesn't mean anything if it can't adjust fast enough, like a falling 22-ton object doesn't afford you time. If a sensor detects a wind gust or a pressure drop, how does the engine react before it crashes?
Right, and that is handled by a deeply integrated 3-layer control architecture. The top layer is the central flight computer up in the rocket itself. Its job is trajectory planning, so figuring out where the rocket is in the sky, factoring in wind shear, and locating the landing pad.
Okay, so that's the big picture brain.
Yeah. Then there is the middle layer, the engine control unit, or ECU. There's the ECU located right next to every single engine. It takes the broad directions from the central computer and translates them into specific commands for thrust and the fuel-to-oxygen mixing ratio.
And finally, the bottom layer consists of the physical actuator, the massive hydraulic valves that actually move the sleeves and control the fluid flow. The source material points out a fascinating detail about those hydraulic valves, actually. They aren't powered by some separate hydraulic system that could leak or fail during the violent shaking of re-entry.
This is one of my favorite details. The hydraulic pressure needed to open and close these massive valves is provided directly by the high-pressure fuel coming off the turbopump itself.
Which is so clever.
Right. They eliminated the need for a separate, failure-prone hydraulic fluid system entirely. If the pump is spinning, you have control pressure. The engine essentially uses its own lifeblood to move its muscles.
I am trying to wrap my head around the sheer scale of the math involved here. The rocket is constantly getting lighter, the wind is blowing, the atmosphere is changing density. Yet the source says the landing thrust is controlled to an accuracy of 0.5%. To hit that precision and ensure the rocket touches down at a speed of under 2 meters per second, the paper mentions high-frequency PID controllers. Before we move on, what exactly is a PID controller doing in this context?
Okay, so PID stands for Proportional Integral Derivative. It is a control loop feedback mechanism. Think of it as the ultimate micromanager for the engine's valves.
So if I'm driving a car on the highway, the proportional part would be seeing I'm drifting out of the lane and steering back. The integral part is realizing my wheel alignment is slightly off, so I consistently have to pull the wheel a bit to the left. And the derivative part is seeing a sharp curve coming up and preemptively steering into it based on how fast I'm approaching. Is that close?
That analogy translates perfectly to fluid dynamics, actually. The PID controllers are dynamically adjusting the valves thousands of times a second to make sure that 20% pressure drop across the pintle injector is maintained, and that the oxygen-to-fuel ratio shifts smoothly from 2.0 early in the burn to that near-perfect 2.7 right at landing.
So it's constantly correcting itself.
Yes. They're looking at the current error, the historical error, and the predicted rate of change all at once.
But the PID controllers are just the micromanagers. The paper also highlights model predictive control, or MPC, running alongside them. And it mentions quadratic programming equations. I haven't taken calculus in a long time. What is this map actually doing up there in the air?
So while the PID controllers manage the immediate physical hardware, the MPC is the macro manager. What's fascinating here is that MPC doesn't just react to what the rocket is doing right now. It is constantly predicting the future over a specific time horizon.
Predicting the future.
Literally. 10 to 20 times every single second, the MPC algorithm calculates the rocket's current speed, weight, and trajectory. And then it simulates the next several seconds of flight.
It's basically playing a video game simulation of the landing, seeing the future, making a decision, and then doing it all over again a fraction of a second later.
That's exactly it.
Yeah.
And that is where the quadratic programming comes in.
Mm-hmm.
It's an optimization problem. The MPC has to balance competing costs. Like, it wants to hit the ground at zero velocity, but it also has to ensure it doesn't run out of fuel while doing it, and it has to stay within the physical stress limits of the vehicle.
So it can't just slam the brakes so hard the rocket snaps in half.
Right. The quadratic equations plot a theoretical curve that satisfies all those constraints. It essentially asks, if I apply this exact thrust curve right now, where will the rocket be 3 seconds from now? It finds the perfect command, executes it, and recalculates the whole thing 50 milliseconds later.
To really understand why this computational speed matters, the source material brings in some context about a different rocket, the Zhuge 3, which suffered a landing failure. What happened there?
Yeah, the Zhuge 3 failure perfectly highlights the razor's edge these systems operate on. According to the data, the Zhuge 3 failed because its engine valves had a response delay of just 0.3 seconds.
Wait, 0.3 seconds? That is less time than it takes to blink your eyes.
Exactly. But in the context of a falling rocket, that 0.3-second delay between the software sending a command and the physical valve actually moving caused an 18% imbalance in thrust.
Oh my God.
Yeah. The software knew what it wanted to do, but the hardware couldn't physically move fast enough to execute the command. The rocket lost control. By contrast, SpaceX demands a system-wide response time of under 0.05 seconds. That is 50 milliseconds.
How do you even develop software that reliable? I mean, you can't just write quadratic programming code on a whiteboard and hope it maps perfectly to real-world fluid dynamics on the first try, right?
You absolutely can't. And that is why SpaceX employs a philosophy they call flight as test. Traditional aerospace treats a crash as a catastrophic failure, like a reason to halt programs for years. SpaceX treats a crash during a test campaign as the fastest possible way to parameterize their PID and MPC controller.
Well, these are gathering data.
Tons of it. Every single Falcon 9 flight is carrying over 2,000 sensors. They are constantly measuring pressure, temperature, vibration, and valve positions in real time.
So every launch, even the routine commercial ones deploying satellites, is secretly a massive data gathering mission. They didn't just build a better engine, they built a flying software iteration lab.
That's a great way to put it. They take all the data from those 2,000 sensors, feed it back into their algorithms, and refine their predictive models.
Yeah.
They find out exactly how the engine behaves in the real world under real atmospheric conditions, like when a valve sticks for a millisecond or the fuel sloshes unexpectedly. And then they just update the software for the next flight.
So what does this all mean? When you take this incredibly robust hardware, the Apollo-era pintle injectors, the fuel-cooled walls, the hydraulic valves powered by turbopumps, and you marry it to this predictive 50-millisecond MPC software loop, what is the actual bottom-line payoff compared to the rest of the industry?
Well, the payoff is a set of performance statistics that completely rewrite the rulebook for liquid oxygen and kerosene engines. If you look at a traditional expendable engine of this type, it can only throttle down to about 60% of its maximum power safely. Its thrust accuracy has about a 5% margin of error, and even the most robust ones are designed to be fired maybe 5 times in their entire lifespan.
Right. They were literally designed to throw themselves into the ocean.
Exactly. Now look at the Merlin 1D. It throttles down to 39% without combustion instability. It has a thrust error margin of just 0.5%. It boasts a staggering 98% successful recovery rate over hundreds of launches. And a single engine can be reused over 40 times.
Over 40 times. That durability just transforms the entire economics of spaceflight. We are no longer throwing away the airplane after a single flight.
Exactly.
But it makes me wonder, if they are already hitting a 98% success rate, what could possibly be left to improve? The paper actually outlines the next frontier for thrust regulation, doesn't it?
Oh yeah, the engineers are far from finished. They're looking at integrating machine learning directly into the adaptive control systems. Instead of just reacting based on pre-programmed physics models in the MPC, the engine could use AI to dynamically adjust its own fuel mixture based on minute, real-time changes in vibration and combustion pressure.
So the engine essentially learns how to run smoother while it's falling.
Yes. They're also looking to widen the thrust range even further, pushing for stable combustion at even lower percentages. And mechanically, they plan to expand the engine's thrust vectoring capabilities.
The steering, basically.
Right. Right now, the physical gimbaling, the tilting of the engine nozzle to steer the rocket, can deflect about plus or minus 5 degrees. The paper notes they want to push that to plus or minus 10 degrees.
And the 10-degree tilt would give the rocket wildly more maneuverability to fight high crosswinds or land on a pitching drone ship in rough seas. It provides a much larger control margin for the flight computer to work with.
Precisely. It just adds another layer of adaptability.
We really have gone on an aha journey today. We started with the visual we all know, a massive tube of metal floating down from the sky, resting on a pillar of flame. But now we know it is not just falling, it is a self-cooling, continuously recalculating machine. Like it is pumping its own fuel through its walls to avoid melting, it's shifting physical sleeves inside its injector to keep the pressure perfect, and it is predicting its own future 20 times every single second to adjust that fiery breath.
It's a stunning symphony of mechanics and mathematics. The software and the hardware are so deeply integrated that they function almost like a biological nervous system reacting to its environment.
The next time you watch a commercial space launch, you're going to see past the smoke and fire. You are going to recognize the millisecond ballet of turbopumps, pintle injectors, and PID controllers, keeping that vehicle perfectly balanced. We want to thank you for joining us on this deep dive. Keep questioning, keep exploring, and keep learning.
And if we connect this to the bigger picture, this raises an important question to leave you with. SpaceX treated early rocket crashes not as disasters, but as vital data for their algorithms. If we can create mathematical models that manage chaotic fluid dynamics, massive weight changes, and fiery explosions with 0.5% precision in less than 50 milliseconds, what other chaotic, rapidly changing systems here on Earth, like global climate modeling or managing our electrical grid during extreme weather events, could eventually be solved using this exact type of predictive, self-correcting logic?